Hello, good evening everyone. We are meeting for the discussion of week 8 mm, problem solving session. So this week we'll be again looking at some questions from shaft misalignment, looseness, rub and all. So for those who are viewing this video or attending the session for the first time, my name is Akhil. I'm a PhD student from IIT Madras. I'll be handling the live samples or problem solving sessions for the course Machinery, fault diagnosis and signal processing during this semester. Let's look at the first question. Shaft misalignment occurs due to which of the following conditions? Looseness of the rotating components or offset present either by lateral or by an angular moment amount or internal crack in shaft or rubbing of the rotating components. So shaft misalignment basically means in general cases you have one shaft that drives the system connected to a shaft that is getting driven. Now if there is any misalignment between these two shafts, that leads to the problem of misalignment if they are not aligned perfectly concentric. So if they are concentric, the central axis of this first shaft or the driving shaft should move through the central axis of the driven shaft. Okay, so this is the prime mover shaft and this is the driven shaft. So if the axis of them are coinciding, that means all the cylinders are concentric, then that is no misalignment. Now if let's say the driven shaft is slightly offset, let's see the case like this. And the driven shaft is slightly below the prime mover shaft. So this is the lateral misalignment or parallel misalignment. So this is one possibility. There is one more possibility where so in this case they are deviated by some angle. So this is angular misalignment. So for the question, shaft misalignment occurs due to offset present either by lateral or by an angular amount. So both are the cases that can actually lead to misalignment. So this happens because when you are actually installing the equipment or the setup, there could be some uneven surfaces or uneven foundations and can result in these different kinds of misalignments. So for this question, both lateral and angular element offsets lead to shaft misalignment. Okay. Now the next question. So these are happening actually due to uneven foundation. Caused by uneven foundation. Now, because of the presence of shaft misalignment, there will be push and pull forces in the shaft. And what will be the direction for this push and pull forces? Axial or radial or both or none of these two? So the shaft misalignment, the push and pull forces caused by the shaft misalignment will be primarily in the axial direction, because as you are seeing here, the misalignment is due to the this misalignment in the axial direction between the two shafts. So this will actually cause push and pull forces in the axial direction, and there won't be any forces in the radial direction due to misalignment. Okay, this push and pull forces will also be in the axial direction. I hope this is clear. Yeah. Next question. Which characteristic of the frequency response represents misalignment in shafts? So, as we discussed earlier in last previous weeks, you do the get the vibration signals and then you perform FFTs on the signals. So, how will the FFT looks if there is a misalignment fault in the shafts? Will it cause axial vibration levels at a frequency of rotational speed, or axial vibration levels at a frequency twice the rotation speed, or it will be a continuous spectrum, or we can't say? So what will be the characteristic frequency response which is caused by the misalignment in shafts? So the misalignment causes push and pull forces in axial direction, as we saw in the last question, and this axial forces will be visible at a frequency twice the rotational speed. Okay, this is because the these axial forces will create the torques on the shafts at twice the frequency or at twice the rotational speed. So because this axial forces creates torques at a frequency twice the rotational speed, in the frequency spectrum also you will see vibration levels at a frequency twice the rotational speed, and you won't see at the frequency of rotational speed. So when you are doing when you get the FFT, you will have one characteristic rotational speed and there will be one more peak at twice the rotating speed, which is due to the axial vibration, and that is due to the misalignment in the shafts. Okay. So the characteristic response of misalignment is axial vibration levels at a frequency twice the rotating speed. So if you are seeing such kind of amplitudes at twice the frequency of rotating speed, then you can say that there is some misalignment issue in the shafts. No. So there is one way to identify the misalignment, or it's called elliptical orbit plot. So when you have this orbit plot, if it is elliptical in nature, what does it represent? Does it represent crack or misalignment or failure of bearings or rotating unbalance? So this orbit plot is actually generated by having two accelerometers perpendicular to each other at the driven end of the shaft. So you have these two shafts. So you can keep these accelerometers here and one here. So if you look from this view, if you look from this side, you will see like on the shaft there will be one accelerometer here and one accelerometer here. Okay, so accelerometer 1 and accelerometer 2. Now if you plot correspondingly these two on x versus y plot, you would actually see some elliptical orbit plot. So if it is elliptical in nature, then that means there is a misalignment in the shaft. Okay. So this orbit plot is generated by having two accelerometers perpendicular to each other at one of the shafts. And when you are noting plotting this x versus y, you will, if you are usually if there is no misalignment, you should get a perfect circle. That represents no misalignment. But if there is any misalignment, you will get an elliptical orbit plot. Okay. So the elliptical orbit plot represents the misalignment of the shafts. Now this misalignment may increase with time due to what are the reasons that can increase this misalignment with time? Options are the corrosion of shims, uneven thermal expansions between the driven and the driver, or both or none. So what would actually cause the increase in misalignment with the time? Corrosion of shims or the uneven thermal expansions between the driven and the driver shafts, or the couplings. So actually both of them will increase the misalignment. So the answer is C, both. So with the time, uh, if there is any misalignment, causes frictional forces between the couplings and the shafts that actually generates temperature, which corrodes the shims. Plus there will be the thermal expansions also. And if temperatures are different, then these thermal expansions would be uneven, and that would also leads to increase in further misalignment. Okay. So the misalignment may increase with the time due to corrosion of shims and uneven thermal expansions between the driven and the driver shafts. Okay. The shaft misalignments are generally avoided with the help of. So what do you actually use when you have, as we discussed earlier, uneven foundations actually lead to misalignments. Now, how can you solve this issue? So, what are the general options? Metal shims, adjusting jack bolts, or flexible couplings, and all of the above. So, what do you think should be used to avoid shaft misalignment? So, the answer is actually all of them. So, metal shims, adjusting jack bolts, and flexible couplings. All of them can be used to avoid the. So, one is metal shims and adjusting jack bolts. So because they are misaligned means there could be lateral or angular misalignment. So with the help of metal shims and adjusting jack bolts, you can bring the other shaft to be in the same axis as the one of the shafts, making them aligned. And flexible couplings will also help in that. So the answer here is all of these three. The shaft misalignments can be avoided with the help of all metal shims, adjusting jack bolts, and flexible couplings. Now, flexible couplings are used for. So flexible couplings can be used only for smaller misalignments or only large misalignments or any type of misalignments or none of these. So as we saw in the last answer, flexible couplings are one way to solve the misalignment. But are they used for small or large is the question. Flexible couplings are mainly used only for small misalignments. So when you have large misalignments, you need to use the jack bolts or metal shims. But if they are very small, then you can use the flexible couplings. Okay. So mainly for small misalignments. So these are the questions with respect to misalignment. We will revise again once. So the first question is, how can a misalignment occur? Whether due to looseness of rotating components or offset present by either by lateral or an angular amount between the two shafts, or the internal crack, or the rubbing of rotating components. So shaft misalignment actually occurs due to the presence of an offset either by lateral or an angular amount, as you see here. So here the central axis of the two shafts are not concentric. There is a lateral deviation between these two. So this is a lateral misalignment or a parallel misalignment. If there is an angular deviation, then it's the angular misalignment. So both are possible, and both of them can lead to shaft misalignment. And the shaft misalignment actually causes push and pull forces in the axial direction and not in the radial direction. And the best way to identify this presence of misalignment is to look for the vibration levels at a frequency twice the rotating speed in the axial direction. So if there are these axial vibrations when you are checking using an accelerometer at a frequency twice the rotating speed, then you can say that there is misalignment in the shafts. One more way to identify if there is any misalignment is to have two accelerometers, keep them perpendicular to each other on one of the shafts, and then plot an orbit plot between these two. If it is elliptical in nature, then it also represents some misalignment in the shafts. If it is perfect circle, then that means there is no misalignment. Okay, so an elliptical orbit plot represents the misalignment of the shafts. Now, will this misalignment increase with time? It does increase with time, and that is due to the corrosion of the shims and uneven thermal expansions between the driven and the driver shafts. So the misalignment, whatever axial push and pull forces, they create frictional forces, and which leads to temperature rise, which then corrodes the shims and causes thermal expansions. Now, what are the steps that you need to do to avoid this misalignment? If you know that there is some misalignment happening, so the some of the ways you can accommodate this misalignment is to have metal shims or adjusting jack bolts or flexible couplings. Okay, so based on case by case basis, you can use one of them. And these flexible couplings are mainly used for cases where the misalignment or misalignment is very small. So only in those cases, flexible couplings you can actually directly use instead of shims or jacks. Okay, so that is it with the misalignment, shaft misalignments. Next, we will go to the next topics. So, if there is an eccentricity, what is true for eccentricity in rotors for electrical machines? So, what will eccentricity in rotors cause, or how will you be able to identify the eccentricity, presence of eccentricity? Through radial vibrations at twice the rotational speed, or axial vibrations at twice the rotational speed, or radial vibrations at rotational speeds, or none of these. So what is the characteristic response for an eccentricity in rotors? eccentricity in rotors actually causes uneven air gaps between the stator and rotor coils. This leads to uneven electromagnetic forces leading to radial forces or radial vibrations, and that too at twice the rotational speed. Okay, so because yeah, so this will be due to radial vibrations at twice the rotational speed, and it is due to the uneven air gap between the stator and the rotor coils, which creates in response uneven electromagnetic forces, and that in turn generates radial vibrations. Okay, so eccentricity for electrical machines actually causes radial vibrations at twice the rotational speed, and it doesn't create any actual vibrations, and not at vibrational speed, it is at twice the rotational speed. Next we look at the cracks in shafts. So what are the type of cracks that grow with time due to fatigue loading? So because of your type of loading fatigue, as you keep the shaft in the working conditions for a long time, for years and years, some certain types of cracks actually grow with time. So, and what are they? Are they internal cracks or the surface cracks or both of them or none? Actually, surface cracks grow with time. If there are any internal cracks, you actually identify them even before you use using ultrasonic techniques. Uh, you identify such shafts and you discard them. But for surface cracks, you can't use this technique. So surface cracked shafts could actually be put in use, and these surface cracks will actually grow with time due to the fatigue loading. Okay. So during the operations, there is a way to identify the surface cracks that we will see in the next question. So what are the type of cracks that grow with time due to fatigue loading? The surface cracks. No. So the presence of first and second harmonics of rotational speed in frequency spectrum is a characteristic of misalignment or eccentricity or cracked shaft. So think about this question, and we know how misalignment and eccentricity already looks. So we saw that misalignment, you will actually have axial vibrations at 2 times the RPM, and eccentricity you will have radial vibrations at 2 times the RPM. So what is left is cracked shaft. And yes, cracked shaft actually causes first and second harmonics of RPM in the frequency spectrum. So that is, let's say if you are doing frequency spectrum and your RPM, let's say, corresponds to this frequency. So at 2F and 3F, there could be some other peaks. So these indicate crack shaft, this presence of first and second harmonics. Okay. So the presence of first and second harmonics is the characteristic of the cracked shaft. Next question. So what if we have bowed or bent shafts? So that is, shafts, instead of being perfectly straight, like this, they might be slightly bent or bowed. Or this is bowed or bent. So if the shafts are like this, what will they cause? Which kind of vibrations they will cause? So as you can see, this bowed or bent kind of cause misalignments. So they kind of cause the axial forces or the axial vibrations. So as we have seen, misalignment causes axial vibrations. So this bowed and bent shafts also can cause axial vibrations. Okay. Next question. In a rotating machine with an unbalanced mass of 10 kgs and an eccentricity of 0.01, rotating at a speed of 10 radians per second, what will be the magnitude of the unbalanced force? 10, 1 or 0.1 or none. So you have a rotating machine and unbalanced mass is given, eccentricity is given, speed is also given. What should be the magnitude of the unbalanced force? And what kind of force does an eccentricity create in rotating machines, axial or radial? It creates radial forces. So if there is any eccentricity, let's take a cylinder or a disc. Okay. Now let's add some extra mass in here. Now as this is rotating with some angular speed omega, what will be the extra force experienced by this mass? So let's say, let's first look at some mass here, m1, and because this is a uniform disk, there will be an opposite m1. And what will be the centrifugal force on this? Mr omega square. So on this also an equal force will act and these two will cancel out each other. But if there is an eccentricity, that means an unbalanced mass, so there is nothing to cancel out the centrifugal force created due to that. So because of that, it will have an extra radial force due to centrifugal. And what will be that force? It is mr omega square, and in this case it will be the eccentricity me omega square. Okay, so what is mass here? 10, eccentricity 0.01, and omega 10 radians per second, so 10 square. So then 10 into 0.01 into 100. So 10. Okay. So unbalanced mass with an eccentricity given and speed given actually creates an unbalanced force of me omega square. Okay. Now, yeah. What would be the direction of action of the unbalanced force in the case of rotor with unbalanced mass? In the case of rotating machine, unbalanced mass, what will be the direction of the force? We saw this in the previous question also. Will this unbalanced mass cause any axial force or radial force or both? So as you are rotating, this presence of extra unbalanced mass creates radial forces. Okay. Yeah. So the direction of action of the unbalanced force is radial in nature. Let's look at the next question. What would be the predominant frequency when you have a rotating unbalance in the frequency spectrum? So with this rotating unbalance, you have your accelerometers and you calculated the FFTs and plotted the frequency spectrum. Now, if it is a rotating unbalance, how will it show up in the frequency spectrum? So wherever it is, it's always like at the frequency of the rotational speed, right? Because the next time it comes to here, it has to follow one full rotation. After one full rotation only, it will be again same force. So the frequency will also be same as the rotational speed. Okay. So the predominant frequency for a rotating unbalance is the frequency corresponding to the rotational speed. Now, will this additional unbalanced force creates any additional load? It actually induces additional fatigue due to the presence of this extra force and can lead to premature failure of which components? Shafts or bearings or both? So the additional fatigue can actually lead to, because this additional forces will be on both shafts and bearings, so both of them will fail. Okay, so the answer is both. Both shafts and bearings, as this unbalanced forces will be acting upon both of these. Next question. Now you have this unbalanced masses and unbalanced forces. In this case, we have a multi-stage compressor or turbine. In this case, if there are unbalanced forces, which planes will they be in? Will all of them be in a single axial plane or different axial planes? So this is a multi-stage compressor or turbine. So you have a single shafts, but a multi-stage compressor, so it might have one setup here and one more here. And one more setup here. So it could have the unbalances creating at different locations. So different axial planes, if you are looking from this side, so these three planes there could be different unbalances. So in a multi-stage compressor or turbine, the unbalanced forces will be usually in different axial planes. Okay. So for a multi-stage compressor or turbine, the unbalanced forces, as we see here, because it has multiple stages and a single long shaft, at each location there is possible for unbalanced forces. So it will have in different axial planes. Next question. Which method of balancing is suitable for balancing these multi-stage turbines? Static balancing or dynamic balancing? So you have these forces in multiple axial planes. What technique will you need to do? So you have this multi-stage setup. Let's see. And you have forces creating or unbalances in different axial planes. So let's say at one instant there will be unbalance creating a force like this, one more unbalance creating a force like this, one more unbalance creating a force like this. So you have forces in three different planes. Let's say if you are trying to balance it from here, you need to balance out this force and you need to balance out the couple also, because if you are looking from here, these two forces can actually create a couple or a moment on the force. So you need to actually do balancing in different planes to solve for forces in different planes such a way that there are no couples or torques generated overall. So multi-stage compressors or turbines actually have unbalanced forces in different axial planes, which lead to unbalanced resultant unbalanced forces and couples. Okay. Now these unbalanced forces and couples you need to balance under each plane. So the technique used is you balance in each plane. So balancing here, one again balancing in this, and again balancing here. So you do multiple balancings. You balance the forces in each axial plane. So at the end there are no forces or torques. Okay. So you are balancing only forces in each plane. But you are doing it multiple different planes. So this is called dynamic balancing. In different axial planes. So once all the forces in different axial planes are balanced, effectively you don't have any actional forces and you don't have any couples also. Okay, so for multi-stage turbines or compressors, you use dynamic balancing. That is balancing forces in different axial planes. But if you have only single stage or just a simple ones, then you have to do balancing only in that axial plane. So that is static balancing. Okay. Okay, let's move to the next question. I hope this is clear. Three unbalanced masses are rotating at a constant speed in a single plane, which is a sufficient condition for balancing. The moments should be balanced, the forces should be balanced, both forces and moments should be balanced, or none. So when you have three unbalanced masses are all in a single plane. So what kind of balancing do you need to do if they are all in a single plane? So if all in a single plane, then only unbalanced forces will be generated, no couples or the moments. It is first thing to notice. And if they are in a single plane, you add extra masses to balance out those forces. So balance the forces in that axial plane. So this is enough. You don't need to worry about any moments. Okay. So just balance the forces. So when you have unbalanced masses in a single plane, if you just balance the forces, then that should be enough. Now if you are there in a multiple planes, then we need to balance forces in each plane, so that is dynamic balancing, and this is static balancing. So the name for such a case is such a type of balancing is static balancing. Next question. Which balancing technique is suitable for radial fans or single stage pump, either static or dynamic? So when you have only radial fans or single stage pumps, so that is like single stage, so you have only a single system, so the forces will also be in a single plane. So if forces, if unbalanced forces in a single plane, then static balancing is enough, right? If you just balance the forces, then in that plane that is enough, so that is static balancing. So what is the balancing technique we use for radial fans or single stage pumps? It's the static balancing. The next question. Which conditions among the below options represents looseness in vibrating machines? So now we have, after unbalanced masses, we are looking at looseness. So if there is looseness in a vibrating machine, how will it look like in the frequency spectrum? What will be the characteristic of this looseness? What exactly is that looseness means? So in general, when you have a shaft, rotating shaft, it may be connected to gears, it can be connected to pulleys, or it can be connected to ball bearings. So a single shaft can be connected to multiple components like gears, multiple gears, not in a single gear, multiple gears, pulleys, bearings, and so on. Now, if they are not tightly connected to the shaft, so if these components are not tightly attached to shaft or locked to the shaft at that specific location, that is here, here, here. If they are not locked exactly there, then they can actually move in the axial direction. Like this pulley, if during the rotations, can actually move to here. So if this moves, then it can actually impact a different component. So this pulley or this bearings or this gear can move and impact this this system. So if they are not locked, that is they are loose. So this is looseness. Then these components can hit one another. So when they are hitting one another, it actually causes impulsive vibrations. So usually this impulsive vibrations, because they are hitting, they will cause peaks at fractional frequencies or fractional harmonics of the rotational speed. And when you have this fractional harmonics or rotational speed and plus their harmonics. So in these cases, when you have looseness in the system, you will actually have in the frequency spectrum peaks at the fractional harmonics of rotational speed and their harmonics. Okay, so looseness basically means whatever are connected to the shaft, they are loosely connected, so they can move across the shaft in the axial direction of the shaft, and when they can move, they can hit one another, and when they are hitting one another, it kind of creates impulsive vibrations, and these will give peaks at fractional harmonics of the rotational speed. Okay. Now let's move to the next question. Yeah, this question is rub. Now, how can we identify a rub? The phenomena of rub can be identified by, again in the frequency spectrum, what will be the characteristic frequency response when you have rubbing kind of fault happening. We'll have peaks at the fractional harmonics, or the peaks at harmonics, or a continuous spectrum. So harmonics basically means, let's say you have frequency of 10 Hertz, 10 into 220, 10 into 330. So these are harmonics. Subharmonics basically mean if you have 10, so 10 by 2, 5, 10 by 3, like that. So these are fractional harmonics, and harmonics will be multiplications, integer multiplications. Okay. Now how can you identify the rub? So rub basically means, let's say you have a shaft connected to a compressor with radial, let's say radial fans in a pump, and this is connected to a casing. Okay. Now let's say this fan is for some reason slightly taller than others. So whenever this fan passes at this location, or the fan is not slightly taller, here it is slightly below. The casing is rubbed with the fans. Okay. So whenever a fan comes there, it actually hits the casing. So this is called rubbing. So when the components as it is rotating is rubbing against the casing, so touching against the casing. So that would be generates rubbing. Now when this happens, you will have this could actually lead to vibrations at subharmonics or fractional harmonics plus harmonics also. Okay, so this could have, because this is hitting and the next one will hit. So actually in a single rotation itself there could be multiple times it is happening, and as one is hitting, if it is uneven during a single hit itself, like let's say impulse is like this, let's say this. So during this fan moving itself, this part can hit and this part can hit multiple times, or they can hit only, like only one fan can hit instead of all the fans. So it is possible to have fractional harmonics plus harmonics. So as all frequencies come up, this will actually lead to a continuous spectrum. Okay. So the phenomena of rub, if it is there, you will actually, instead of getting peaks, you will get a very continuous spectrum, like all the frequencies are showing up. So that's how you can identify the phenomena of rub. Okay. So harmonics happen when multiple fans touch in a single rotation, or fractional harmonics happen, let's say only one fan touches and sometimes it doesn't touch. So all are possible, and that's what gives you a continuous spectrum. Now we have done with looseness and rub. Let's move on to journal bearing. Works on the principle of which kind of lubrication. So what are the main types of bearings which we have? We have ball bearings and we have this journal bearings. So ball bearings are very smooth. They work with anti-friction or rolling friction. Basically very reduced friction. And journal bearings work with fluids. So they actually work with hydrodynamic lubrication. So journal bearings work on the principle of hydrodynamic lubrication. Next question. The vibrations of the bearing can be reduced by. So why actually the vibrations are in the bearing are produced? How? So let's say the bearing, instead of being perfectly smooth like this, let's say it has a wavy pattern like this, or it's not smooth. So this wavy pattern or rough surface could actually create vibrations. Okay. Now how can you reduce those vibrations? So if you smoothen the surface, so if you make it as close to perfect sphere or circle as possible, then these vibrations are actually reduced. So you'll get a smooth surface, or you'll minimize the vibrations of the bearing. Okay. Next question. So this should be straightforward and similar to the last question which we discussed. Surface waviness and roughness leads to vibrations in bearings. True or false? The answer is true, as we see in the last question. The surface waviness and the roughness actually leads to vibrations in the ball bearings. So this is the last questions for today. If there are gear vibration signal, it is, if you are looking at accelerometer with a and using a gearbox, so the gear vibration signal, you will have family of side bands around the gear meshing frequency and its harmonics. Is that true or false? So when you have gear vibration signal, so you'll have family of sidebands around the gear meshing frequency, sure, and you will also have its harmonics. So answer is true. And if there are any faults in the gear, so you will see higher amplitudes for the harmonics or the sidebands. So that's how you can identify the, if there are any faults in the gear. Okay. So that is the last question. So one more question before we leave. We'll look at unbalanced mass again. Let's say unbalanced mass of 5 kg and eccentricity of 0.1 and the RPM is 600. So what is the magnitude of the unbalanced force? So as we saw earlier, the magnitude of the unbalanced force would be me omega square. So unbalanced mass is 5, eccentricity 0.1. So RPM is 600. So you need to convert that to radians per second. So 600 into rotations per minute. So 2 pi 60. So one rotation is 2 pi radians and per minute, so 60 seconds. So this is equal to 20 pi rads per second. So 20 pi whole square. So 0.5 into 20 into 2400 into pi square. So 200 pi square is the magnitude of the unbalanced force. Okay. So before closing, I will just revise today's setup. So how does shaft misalignment occur? Shaft misalignment occurs due to any offset present either in bilateral or an angular amount. So if the driven or the prime mover and the driven shaft, if their axes are perfectly concentric, then there is no misalignment. But if there is a lateral deflection between these two, then that leads to lateral or parallel misalignment. But if there is an angular deviation, then it leads to angular misalignment like this. Okay. So it is caused by both offset due to present either when a lateral or when angular moment. Now if there is, and this misalignments are possible because of the uneven foundations when you are doing the installation. Now this shaft misalignment actually causes this push and pull forces because they are not aligned perfectly, and these forces will usually be in the axial direction and not in the radial direction. Okay. Now, which characteristic frequency response represents misalignment in the shafts? So as we have seen, it creates axial vibration levels, and in this case, in the misalignment, let's say it's angular misalignment. So when it is, let's say this or this, will create same level of torque on the system. So in because of that, you will have vibration levels at a frequency twice the rotational speed. Okay. So in misalignment on shafts, you can identify it by looking at the axial vibration levels, and if there is a presence of a peak at frequency twice the rotating speed, then it represents a misalignment. Now there is one way to identify the misalignment, that is by generating an orbit plot, that is generated by placing two accelerometers perpendicular to each other at one end of the driven shaft, and then plot the magnitudes of each other. Now if the orbit plot is perfectly circular, that means there is no misalignment, but if it looks like an ellipse, then there is a misalignment. Okay. So an elliptical orbit plot indicates the misalignment of shafts. And this misalignment can actually increase with the time, because this when there is some small misalignment, you add this metal shims or bearings or jack bolts. If the misalignment is there, because of that there will be frictional force, axial forces, which will in turn generate frictional forces, which raises the temperature, which then can speed up the corrosion of the shims, and there also, because of the temperature, is uneven thermal expansions between the driven shafts and the bearings and everything. So misalignment can actually increase with the time, okay, due to corrosion of shims and uneven thermal expansions. Next, now how to avoid this shaft misalignments? What are the best practices? So the best practices are to use metal shims or adjusting jack bolts or flexible couplings. So these three are some of the ways through which you can avoid the shaft misalignments due to the uneven foundations. So if you know that there is an uneven foundation, if they are not becoming concentric, the driven and the driver shaft, then you try to use these metal shims or adjusting jack bolts to make them perfectly aligned. And there is one more important point to remember. These flexible couplings, they are only suitable for the cases where the misalignments are small. If it's a large misalignment of larger magnitudes, then you need to have extra shims or jack bolts. But if it is very small in nature, then if you have flexible couplings, that is enough. And yeah, so how will eccentricity in rotors characteristically look in the frequency spectrum? So if there is an eccentricity, then it creates uneven air gaps between the stator and rotor coils, which in turn generates uneven electromagnetic forces and the corresponding torques. So there will be radial vibrations at twice the rotational speeds. So if there are radial vibrations at twice the rotational speeds, then you can say that there is some eccentricity in the rotor. And if there are axial vibrations at twice the rotational speeds, then it is the shaft misalignment. Next we have the cracks. So if the cracks are internal, usually you identify them even before you use the shaft by using ultrasonic techniques and discard those shafts. And if there are any surface cracks, those you can't identify with these ultrasonic techniques, so you have to deal with them. But these surface cracks actually grow with time because of the fatigue loading. Now, how can you identify this cracked shaft in the frequency spectrum? So if there are first and second harmonics of the rotational speed in the frequency spectrum, then that indicates it's a cracked shaft. Okay. Next, if you have bowed or bent shafts, they create these vibrations in which directions? Axial or radial? As we have seen earlier, if there is an eccentricity, then you get radial forces, but if it is misalignment, then you get axial vibrations. So bowed or bent usually gets closer to misalignment, so they kind of generate axial vibrations. Now, now we move on to the unbalanced masses. If you have a rotating machine with an unbalanced mass of 10 kgs and an eccentricity of 0.01, rotating at a speed of 10 radians per second, what should be the magnitude of the unbalanced force? So if you have an unbalanced mass, then the force is mr omega square, r or E being the eccentricity. So with that you can actually calculate the unbalanced force. Okay. Now, if there is this unbalanced force, what is the direction of this action of this force? So this unbalanced force is actually due to the centrifugal force on the unbalanced mass, so it will be radial in nature. And what is the predominant frequency for a rotating unbalance? So when you have rotating unbalance, it actually repeats every one full rotation. So you will have frequencies corresponding to the rotational speed only. Okay, and that is in the radial direction. Now, if the unbalanced force induces additional fatigue and leads to premature failure. So if there is any unbalanced force, then it acts on both the shafts and the bearings. So due to that, it could lead to premature failure of both shafts and bearings. Now, how to balance these unbalanced forces if you have those, because they lead to these failures, how to solve from that? So you balance them out in the different types, and if you have a multi-stage compressor, usually these unbalanced forces will be in different axial planes based on wherever these different stages are. each stage might have its own unbalanced forces in that axial plane. So in a multi-stage compressor, usually be different axial planes. Now, if you have these multi-stage turbines, then what is the technique that you use? Use something called dynamic balancing, where you go to each axial plane and then balance the forces in that axial plane. So as you do that for all the planes, then there are no unbalanced forces and unbalanced couples in total. So this method is called dynamic balancing. So if you don't do the balancing, if there are forces in different axial planes, that can actually lead to unbalanced forces and couples. But if you go to each plane and balance them out, then there are no forces, unbalanced forces in any axial plane, so there won't be any couples also. So that is dynamic balancing. Now, in this question, we have three unbalanced masses rotating at a constant speed in a single plane. So that means all the forces are in a single plane. Then if you just balance out the forces, or you should balance out the moments, or both should be balanced. So if all the forces are in a single plane, then that means you don't have any moments or couples to begin with, so you should just balance out the forces. The couples generate because you have unbalanced masses in different axial planes. And even in that case, you go to each plane and you balance out the unbalanced mass or the unbalanced force in that plane. So that way, at the end, you will not have any moments also. They also get taken care of. So when you do balancing in a single plane only, then that is called a static balancing. Yeah. So which balancing technique is suitable for radial fans or single stage pumps? So because this is single stage, there is only one axial plane in which unbalanced forces are generated. So use a static balancing technique. Which condition among these can represent looseness in a vibrating machine? So when you have looseness, uh, a single shaft connected to multiple components like gears and pulleys and bearings, this looseness means these connected components can move axially along the shaft, and when they are moving during the operation, they can hit one another. So because of that, they can generate impulse vibrations because of this looseness, and these impulse vibrations usually occurs at fractional harmonics of the rotational speeds and their harmonics. Okay, so peaks at fractional harmonics of rotational speed and its harmonics is how you can identify the looseness. Next, you have rubbing. So rubbing is when there is one of the component is rotating components is touching the casing periodically. So that is rubbing. So when rubbing happens, based on case to case, you could actually have fractional harmonics and the harmonics also. So at the end, you will actually see a continuous spectrum. So if you are seeing a continuous spectrum in your frequency response, then the fault is could be rubbing phenomenon. Next we have bearings. So journal bearings works on with fluids. between the shafts and the next connected system. So they work on the principle of hydrodynamic lubrication. And if you have ball bearings, they work on the rolling friction, where basically the friction between the connection is very minimized. Now these vibrations at the bearings are actually created due to wavy patterns on the surface of the bearings or due to the surface roughness. So if you smoothen the surface, you can actually reduce the vibrations of the bearing. Next, this surface waviness and roughness, as I said, actually leads to vibrations in the bearings. Now, when you have a gear vibration signal, you will have a family of sidebands around the gear meshing frequency and their harmonics. So that is a characteristic of a gear vibration signal. So we have one more question where we have unbalanced mass and calculate the unbalanced force. So that is it for today, and we'll meet again next week. Thank you.